let's consider oxidation states. Oxidation states are convenient charges. What I mean by convenient, they could be real charge, but in many instances they're a fictitious charge. But it's used to predict the electron transfer that occurs in an oxidation reduction reaction. So we're going to assign each atom in a molecule an oxidation state and see if that oxidation state changes during the reaction, and that will tell us if electrons have been transferred. So in this top reaction that we looked at before, it's easy to see at a glance that zinc lost 2 electrons and that copper gained 2 electrons in this reaction. But in this bottom reaction, just by looking, it's really difficult to see which atoms have lost electrons and which atoms have gained electrons. So we need a set of rules or a convenient way to be able to monitor the electron transfer in more complicated reactions. And so oxidation states is a way to do that. So when we assign oxidation states, the oxidation state will be like a charge, and for atoms, the oxidation state is equal to the charge on the atom. So if we have just an atom, say zinc, solid, and copper 2+, for the reaction, the oxidation state of zinc here would be 0 because it's an atom and it has no charge. The charge is 0. Now for copper 2+, it's an atom, and so its oxidation state would be equal to its charge, so its oxidation state would be 2+. If we had, say, the chloride minus ion, it's an atom, and so its oxidation state would be its charge, and its charge is -1, so its oxidation state is -1. Now if I have an element, oxidation states on elements are 0. So if I have the hydrogen element, so I have 2 hydrogens bonded together, then each of them would be assigned an oxidation state of 0 because it's in an element. If I had oxygen, O2 element, the oxidation state for each oxygen would be 0. So if I have an element, the oxidation state of each atom in the element is 0. So I would assign these two first, elements and atoms, and then go through my hierarchy for atoms and molecules. So first we assign the hydrogen atoms. So we look for hydrogen atoms in molecules, and if hydrogen is bonded to a nonmetal, it's equal +1. So an example for this would be, say, the water molecule. So in this case, oxygen is a nonmetal, so we would assign an oxidation state for each hydrogen as +1. So we have the water molecule here. So each hydrogen atom would have an oxidation state of +1. Now, if hydrogen is bonded to a metal, then its oxidation state is -1. As an example, let's consider arsine. It's arsenic metal with 3 hydrogens bonded to it. And so in this case, each hydrogen would be assigned an oxidation state of -1 because oxygen's bonded to a metal. Okay, so the next rule is group 1 atoms equal +1 and group 2 atoms equal +2. So an example of group 1 atom, say we have sodium chloride. Sodium is in group 1, so we would assign it an oxidation state of +1. Say we have sodium superoxide. We would assign sodium +1 oxidation state. So an example for group 2, say if we have magnesium chloride, magnesium is in group 2, and so we assign it an oxidation state of +2. Magnesium nitrate, magnesium is in group 2, and so we would assign magnesium a +2 oxidation state in this molecule. IF3, then the fluorine is smaller than the iodine, less number of electrons, and so the fluorine would take precedence. So we would assign each fluorine atom a -1 and then assign the iodine what's necessary to balance the charge. Or if we had IF, we would assign the fluorine atom -1 first and then the iodine second. Now for the oxygen atom, if we have oxygen in a molecule, we would assign its oxidation state as -2. So most oxygens have an oxidation state of -2. So say if we had the carbon dioxide molecule, we would assign the oxygens an oxidation state of -2 each. So let's take our water as an example. So we would assign the hydrogen first. So I'm going to assign the oxidation state for each atom on the below the atom, and on top of the atom I'm going to give the sum for all the atoms. So each hydrogen atom is +1. So that means we have +2 total because we have 2 hydrogens. So the oxidation state of hydrogen is +1. We have 2 of those, so that gives a total of +2. Now we assign the oxidation state of oxygen. Well, one rule is the sum of the oxidation states must equal the charge on the molecule. So if we have +2 total now from the hydrogens, we're going to have -2 total on the oxygen because the total charge on the water molecule is 0. So +2 -2, that gives 0, which is the same as the charge on the molecule, 0. So in this case, oxygen has to be -2. As we saw from our rule, is mostly -2. But what if we had this example? Now you've heard of hydrogen peroxide. You can buy it at the store. And we assign hydrogens before oxygens, and so we would assign each hydrogen to have an oxidation state of +1. That means we have a total of +2 for both hydrogen atoms. That means that the total on the oxygen atoms has to equal -2 to give a total charge of 0, because the charge on the molecule is 0. So that means that since we have 2 oxygens and the total is -2 on oxygen, each oxygen atom has to be -1. Let's look at another example. Let's look at the sulfate ion. In this case, we don't have any hydrogens, no halogens. So the first atom we get to assign an oxidation state is oxygen, and by default we'll assign oxygen -2, and so we have 4 oxygens, so that means that we have a total of -8 for all the oxygen atoms. The charge on the molecule is now 2-, so that means the sum of the oxidation states have to equal -2. So sulfur, here the total for sulfur has to be +6, because +6 minus 8 gives -2, which is the charge on the molecule. So that means since we only have one sulfur, each sulfur has an oxidation state of +6.